Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
What if I told you that the next big battery revolution may not come from rare lithium mines, but from the same element found in ordinary table salt? A sodium-ion battery does not use lithium, cobalt, or nickel in many designs, and some latest sodium-ion cells can reach around 175 watt-hours per kilogram with strong cold weather performance. CATL has claimed its Naxtra sodium-ion battery can retain about 90% capacity at -40 degrees Celsius and achieve over 10,000 cycles in its announced design. Inside this factory, one of the most important technologies of the clean energy future is being manufactured. At first glance, it looks like a lithium-ion battery plant. There are long coating machines, giant drying ovens, and precision rollers, automated stacking lines, vacuum chambers, electrolyte filling machines, formation racks, and final testing stations. But there is one major difference. This factory is not making lithium-ion batteries. It is making sodium-ion batteries. Batteries that use sodium ions instead of lithium ions to store and release electrical energy. Sodium-ion batteries work on a similar principle to lithium-ion, but their supply chain is different, often using aluminum collectors on both electrodes. The global battery industry is growing at an extraordinary speed. Electric vehicles, solar farms, wind energy, and data centers all need batteries. Lithium-ion technology is powerful, but it depends on complex supply chains for lithium, graphite, nickel, cobalt, and copper. Sodium-ion batteries offer a different path. They use abundant sodium and generally do not rely on cobalt or nickel. The International Energy Agency reports that sodium-ion batteries may have production costs up to 30% lower than LFP batteries in some scenarios. But it's not a magic replacement. Its biggest weakness is lower energy density, around 175 watt-hours per kilogram compared to 255 for NMC lithium-ion. So while they may not dominate luxury EVs, they are extremely important for grid storage, two-wheelers, and cold climate vehicles. A sodium-ion battery has 5 major parts: the cathode, the anode, the electrolyte, the separator, and the current collectors. During charging, sodium ions leave the cathode and move into the anode. During discharge, they move back, releasing electrical energy. Manufacturing quality is everything. A tiny moisture defect or metal particle can reduce capacity or even create internal short circuits. The production journey starts with raw materials like layered transition metal oxides, polyanionic compounds, and hard carbon. Unlike lithium-ion, sodium-ion batteries often need hard carbon, a disordered form of carbon with a maze of tiny pores for larger sodium ions. Next, active powder is mixed with binder and solvent to form a thick paste called slurry. This must be perfectly uniform with no air bubbles. The slurry is applied to aluminum foil at a thickness thinner than a human hair. This decides the battery's capacity and cycle life. After coating, the electrode enters a long drying oven to remove solvent. This can take up to 24 hours to ensure zero residual moisture. The dried electrode is then calendared, compressed between heavy rollers to achieve the perfect balance of density and porosity. Next is slitting and notching. Every cut must be burr-free, as a tiny metal sliver could pierce the separator and cause failure. In the dry room, moisture is the enemy. Robots stack the cathode, separator, and anode to create the physical architecture of the battery. Metal tabs are welded to the collectors before the cell is inserted into its pouch, prismatic case, or metal cylindrical can. Under vacuum, electrolyte is injected. It must penetrate every microscopic pore, or dry spots will reduce the battery's life. Formation is the first controlled charge. This 24-hour process teaches each cell how to become a battery by developing a protective SEI layer. Every cell is monitored during aging for defects. A modern factory is also a data center, tracking millions of points for safety. Approved cells are connected into modules and managed by a BMS to protect against overcharging, overheating, and imbalance. Scaling is happening now. CATL recently signed a massive 60 gigawatt-hours deal to supply sodium-ion batteries for stationary energy storage. Challenges remain: lower density than lithium, nascent manufacturing maturity, and a supply chain currently concentrated in one region. The future may be multi-chemistry: lithium-ion for energy, LFP for cost, and sodium-ion for safe, scalable, and affordable storage. Next time you see salt on your table, remember, That same element may soon help store the clean electricity of our future. If you enjoyed this engineering documentary, subscribe to Simple Guyane for more videos on industrial technology and future energy systems.